Okay, moving on to the classification portion of the exam. So first we're given some true and false problems. So firstly, a binary, so a 0-1 classifier that always predicts 1, can get 100% precision, and its recall will be the fraction of 1s in the training set. Okay, so this one is false. But let's revisit the definitions of precision and recall. Okay, so precision is defined as the number of true positives over the number of true positives and false positives. Okay, whereas recall is defined as the number of true positives over the number of true positives and false negatives. Okay, so if our classifier is predicting everything to be a 1, the number of false negatives will be 0. Okay, because a false negative is when we predict 0, but the true value is 1, right? So if there are no false negatives, recall will just be TP over TP, which is 1. So that's the opposite of what the question is saying, because it's saying the recall will be the fraction of 1s in the training set, but here the recall would actually be 1. The precision would actually be the fraction of 1s in the training set, okay? Because false positives would be the ones that were truly 0, but we predicted 1, right? And since we're predicting everything to be 1, true positives plus false positives will just be the total number of points in our training set, and so therefore the precision will just be the fraction of our training set whose true value was 1. Okay, so this one was false. B, if the training data is linearly separable, we expect a logistic regression model to obtain 100% training accuracy. That's true. Okay, let's draw a small picture. So for example, if we have our points looking something like this, where this is clearly linearly separable, where this is y is 0 and this is y is 1. In any case, we can always draw some logistic curve like this, and therefore, at least in terms of training accuracy, logistic regression will be able to obtain 100%. C, we should use classification if the response variable is categorical. Again, that's true. And the reason for that is because the whole point of classification is, given some data point or feature matrix, we want to try and predict the label or the class of a certain test point, right? Is a dog or is not a dog. LeBron's shot goes in or shot does not go in. A lot of the times here, we're predicting 1 and 0, but those numbers are arbitrary, right? 1 and 0 could really mean anything, okay? So that's true. The whole point of classification is when our outputs are categories. Okay, D, a binary classifier that only predicts class 1 may still achieve 99% accuracy on some prediction tasks. That's also true. And it's because we never know what the distribution of the points we test our classifier on will be, right? So suppose our classification task was predict if this person is a billionaire, and class 1 means they're not a billionaire, and class 0 means they are. If you just passed in a point and always predicted 1, there's probably greater than 99% chance that the person is not a billionaire, right? So even though we're always predicting 1, our accuracy will be in the range of 99%. Okay, so it really depends on the distribution of 1s and 0s in the points you're testing it on. Okay, so that's true. Just because it predicts 1 doesn't mean it can't achieve an accuracy of 99%. Okay, 37. We're given this plot of two-dimensional points along with the class, and the question is, without additional feature transformations, is this linearly separable? And the answer to that is no, and that's because there's nowhere that I can draw a line of the form y is equal to mx plus b, or I guess in this case it would be x2 is equal to mx1 plus b, right? There's nowhere that I can draw a line such that all the points on one side of the line belong to class 1 and all the points on the other side of the line belong to class 0, right? That just doesn't work anywhere, okay? And it's if you try and draw a line, you'll see it's not possible. So this one is no. Okay, now in 38, we perform fourfold cross-validation on 4 different hyperparameters. Seems like we're trying to pick a value of lambda. Which lambda should we select? Okay, so what we want to do here is look at the column averages, right? Because the column averages tell us the average mean squared error for each of these choices of lambda. The row averages, so these values, don't really tell us anything, okay? Because what we want is to choose a choice of lambda, right? So we want to look at the errors for the different lambdas. And what we see here, the lambda with the smallest error is lambda is equal to 0.2, right? Because 77.775 is smaller than the other three options. Okay, so here our choice is lambda is equal to 0.2. 39, we have some more true and false questions. Okay, A, if no regularization is used and the training data is linearly separable, the optimal model parameters will tend towards positive or negative infinity. That's true, and I have two ways of sort of interpreting this. Okay, so firstly, suppose we have some set of linearly separable points. Okay. And again, some set of points is linearly separable if I can draw a hyperplane, so a line that will, separate the points, right? So here, our points just have one dimension, which is just they lie on the real number line. So I need to draw a degree 0 line, or a line of the form x is equal to a to separate them. It turns out there's infinitely many lines that I can draw here, right? One way to think of that is if, I don't know, for example, x is equal to 5 is a hyperplane that separates these data, so will x is equal to 5.001 and, so on and so forth, right? There will be infinitely many hyperplanes that I can draw to separate these 2 points. So that's one interpretation. Another is, again, suppose I have linearly separable points. And this is actually the same representation as the one I had before, where they were all on the x-axis, but now I'm representing this to be y is equal to 0 and this to be y is equal to 1. I realize now in the previous example that I just drew, I probably should have colored the points on the right to be a different color. But anyways, if our data is linearly separable, what we will eventually get is some logistic regression curve where theta approaches infinity, or if it's the opposite, where the y is equal to 1 points are on the left and y is equal to 0 points are on the right, you'll have theta goes to negative infinity, okay? And all this is talking about is how theta affects the shape of our logistic regression curve, okay? So if you take a look at the textbook, you'll see an example, but the value of theta determines how sharp or steep this logistic regression curve is. So a small value of theta will be something like this, right? Really shallow. It's not changing very quickly. Whereas larger values of theta will make the jump between y is equal to 0 and y is equal to 1 sharper, okay? And if our data is linearly separable, theta will keep on increasing, right? Because the loss will keep on decreasing until it's totally separate and we reach 100% training accuracy, okay? Which is possible when our data is linearly separable. And if that wasn't that clear, I apologize, but I encourage you to take a look at the textbook because it's a little more clear on this subject. But either way, the answer for this one is true. Okay. B, after using L2 regularization, the optimal model parameter will be the mean of the data, since L2 regularization is similar to the square loss. Okay, so this is false. The idea of this question is to sort of trick you, because we often think of L2 regularization and L2 loss and the mean as being related. Okay, but that's actually only true for a very specific case, and that case isn't even dealing with regularization. Okay, so what we think of when we think of L2 loss and the mean is when we're using the constant model, y is equal to theta, and we're using L2 loss here, not L2 regularization. Now, this question is talking about L2 regularization, so like, a plus lambda times the sum of, theta k squared, where k is going from 1 to d. That's what this question is talking about. Okay, which has nothing to do with the L2 loss and the constant y is equal to theta model that we've seen, pre-midterm in this class. Okay, so this one is false because This constant y is equal to theta model really has nothing to do with logistic regression. Okay, so that's false. C, L1 regularization can help us select a subset of the features that are important. That's true, whether or not we're using logistic regression. Recall, part of L1 regularization or lasso regularization is that it sets many of the weights in our theta vector equal to 0. Okay, and again, the textbook has a better explanation of why that's the case, but L1 regularization encourages sparsity. And again, all that means is in our optimal theta hat vector that we end up solving for, through gradient descent or whatever, we will have lots of zeros in here. They won't all be 0, right? Because it wouldn't really be telling us anything if they were all zeros, but many of the entries in here will be 0. Okay, cool. D, after regularization, we expect the training accuracy to increase and the test accuracy to decrease. So this one is actually false. And in general, we would probably expect the opposite to happen. Okay, so when we regularize our model, we make it more general. Okay, and the point of that is so that it generalizes better to unseen data, right? Because we have all of the training data available to us, and if all we care about is training accuracy, we can make our model hyper-specific and overfit to our training set, right? But the whole point is we want to make our model generalize well to unseen data. So by regularizing our model and making it less complex, the training accuracy will actually decrease, so it'll be worse on the training set. But the idea is, in general, the test accuracy will increase because our model will be more general and it generalizes better to unseen data. So this one is false, okay? And lastly, question 40, suppose you're given the data set consisting of n pairs of x comma y, where xi is sort of our input and y is either 0 or 1, that's a response or output. The value of the probability that y is equal to 1, given that x is negative 1, is likely closest to which of these? Okay, so why don't we draw a line at x is equal to negative 1, right? And now what we want to estimate is the probability that y is equal to 1 at this line. Okay, so right off the bat, we can get rid of negative 0.95 because the probability can't be negative. Okay, and as you see, our options, 2 of them are very extreme. Either we're very certain that y is equal to 1, or we're very certain that y is equal to 0, right? In that case, we're not certain at all that y is equal to 1. And the third option is that we're really unsure. It really could go either way. And if you see the distribution of points around x is equal to negative 1, they're pretty evenly spread between y is equal to 0 and y is equal to 1. They're definitely not skewed in such a way that we're very certain that y is either 0 or 1. It's pretty evenly distributed between the two classes. So that's why here we would probably guess that y is equal to 50% because we're really not sure which class our point belongs to. Okay, and that's the classification portion of the exam.